Yeah, so recording has started again and we are back. So yeah, if you have any doubts. Okay, so then let us start again. Okay, so what are the components do you think that would help us to implement these two criteria? That there will be no direct path when the input is 0 or 1, logic 0 and logic 1. Giridhar,
Yes, sir.
yeah, can you comment on this?
I'm not exactly sure, sir.
You're not exactly sure. Okay, maybe you can guess. No guess?
No, sir. I'm
Okay, fine. Okay, so see here, what can we probably do? Say, okay, now why we are doing is, you will understand just in a while. But say, let us make a circuit something like this, as shown here. Okay, and see how this particular circuit can mm, generate these two criteria. Okay, or fulfill the requirements of these two. Let's see this. Okay, so here you see what we have done here. This is one PMOS. So this PMOS has been connected like this. This NMOS has been connected like this. And two inputs has been shorted, like both gates inputs are shorted, right? And it is connected with the input part, right? This is VDD, this is V output, this is CL, load capacitance, right? Okay. So far so good. So here, this is drain, this is source, this is gate, right? For this, and for this transistor, this is gate. So what would be this terminal? Source or drain? For PMOS, yes, it is source, it is drain. So it is source, it is drain. So same current ID has to flow through both these transistors, right? I am saying the DC current, obviously. The DC current has to flow through both the transistors, if there is any. Now, okay, just to discuss why this circuit is how this circuit is working. Again, type of recap, and that will be helpful. So, if you see, let us look from the construction point of view. Okay, MOSFET construction point of view. So, this is NMOS, quite well known. You know that. So why you're discussing this, we will understand all of it, right? You will understand right now. So it is N plus, N plus. So this is the oxide layer. This is the gate metal or polysilicon layer. This is source, drain, gate. You apply here positive voltage, then the channel would be created, right? You apply it more channel would be created, right? So that means when you increase this this positive voltage at this gate terminal with respect to source, right? Your this will means the ID will keep on increase. Okay, right. So this is P type of silicon, right? So you are getting inverted and making this N channel. Okay, now let's consider for this PMOS case, right? So for PMOS case, the construction is something like this. This is P plus, this is P plus, this is N silicon, this is oxide, this is the gate metal or polysilicon, and these are these three terminals, right? Okay. So here, as we are here, if you have to attract hole, so obviously, or make a channel here, right? Then you have to apply a negative voltage. So you apply negative voltage, hole will be accumulated here. Apply more negative voltage, more hole will be accumulated here. That means more will be the current. So more will be the negative voltage, the current will increase, right? Even though there is one more terminal, which is the body terminal for both NMOS and PMOS, but as of now, we will keep these two terminals all bit towards the side. Okay, we will not discuss what is the effect of this potent body terminal potential. Okay, just we will consider this three terminal as of now. Huh? This one is right. Okay. So see here what is happening when you have given say V input equal to logic 0. Okay. So when V input is logic 0, this is gate to source voltage. So gate to source voltage, and for this, okay. So let me write also one more thing here that would be useful. So for NMOS, threshold voltage is positive. Right, that you can understand. You have to apply positive voltage only to create the channel. So threshold voltage is positive. And we denote it as VTHN. Okay. Threshold voltage of N channel transistor. And here the threshold voltage is negative. Right? That also quite clear. You quite from here that you have to apply obviously negative voltage to attract the hole, create the channel. Right? So it is negative, and we will try to represent it like this. VTHP for this P type. Huh? Okay. So when you have applied logic 0, that means basically a 0 volt, you can say, right? Then this transistor, like for this NMOS, then NMOS gate to source voltage is 0. So obviously this NMOS is off, right? So this NMOS is off. Okay. Now see, let us see what is happening to this PMOS. Okay. So you have applied here 0 voltage. So gate is 0. Source is say VDD is equal to 5 volt. So VGS, right? VGS is equal to how much for this? So VGS equal to 0 minus 5 volt. So which is equal to minus 5 volt. So its threshold voltage is negative, and as you make more and more negative, the current will increase. So obviously here this transistor is on and it can conduct current, right? So what will happen? There is a direct path from VDD to this capacitor. So the capacitor can charge. But when this logic is at when this input is at logic 0, you see as this NMOS is off, so there is no path from VDD to this ground, right? So no steady state power dissipation. Only the power will be consumed just to charge this output capacitor, right? Okay, let's see the other case. So now consider this input is at logic 1. So when this input is at logic 1, say here this equal to 5 volt. So now we have applied here 5 volt. So VGS, okay, VGS is now equal to 5 volt, which is much higher than the threshold voltage of this transistor. So then this transistor would now be on, right? But what about here? So here now you have applied 5 volt. So this is 5 volt and this is also 5 volt. So that makes VGS equal to 5 minus 5 equal to 0 volt. But you see for PMOS threshold voltage is negative. But here VGS is equal to 0 volt. So this transistor, this PMOS transistor would not be on. So PMOS is now off. So now as a result, you can see this capacitor which was earlier charged to VDD, right? Now it can discharge through this NMOS. But when this capacitor is discharging, you don't have a path from VDD to ground, right? So that way, the steady state power dissipation, that issue is been solved. I think I said couple of places it is steady state. Actually, it is the static power dissipation. It's not the steady state power dissipation. Okay, static power dissipation. Static power. because I think once I said like it's a dynamic power distribution, so dynamic and steady state. So two contradictory, but it is referred. This term is referred as static power dissipation, right? Static power dissipation. This issue is solved, right? Okay. So please tell me if you have any doubt for this CMOS inverter, like whatever we have discussed as of now. Okay. So if you have no doubt, then let me ask you why we have chosen pull-up network, the PMOS. Why we can't choose NMOS as a pull-up network? And I am expecting some answer from your side. My very simple question is, see here, this is the pull-up network, right? The pull-up network we have chosen PMOS. So my question is, why can't we choose NMOS as pull-up network?
If we choose NMOS as PMOS as pull-up network, then basically the source of the NMOS is floating. So we can't actually write those VGS equations in that NMOS.
Is it so? Okay, let's see that what Shubham you are saying. Okay, so say
I mean, we don't know it. It is in. It will be in triode or saturation or in cutoff region. We just don't know about that. So
okay,
if
okay, okay. Yeah, I think I understand your point, but let us see. Okay, here, this is interesting. Yeah, Shubhayan, very good that you thought in that way. Okay, so say we are using an NMOS. Okay, here. So NMOS has pull-up network. Huh? So we have used here VDD, and this is basically the V in. So it is expected we have something below, which is we as of now we do not know. So it is pull down network, and maybe it is controlling the pull down network that we do not know. What is a pull down network as of now, right? But we are using NMOS as pull up. So NMOS as pull up means this capacitor, let us say that initially discharge, no voltage across this capacitor, right? Okay. Now, when we have given logic 1 at this V in, right? So this is gate. What is this terminal? Source or drain?
drain.
Drain.
Drain. This is source, right? Okay. So when you have given logic 1, say 5 volt, well, let us say VDD equal to 5 volt. Okay. So it is 5 volt. So when you have given logic 1, that is the 5 volt, equivalent to 5 volts. So this transistor would be on or off. This NMOS would be on or off? Off. Shubham?
On, sir.
On, right? So this transistor is
So
on. Yeah, this transistor would be on, right? Okay. So as this transistor is on, so it will charge the load capacitance. Right? So load capacitor output voltage will increase. So what's wrong in this? It will work.
But we want an inverter. This won't act
So
as
yes,
an
sir.
inverter.
Yeah. Obviously, obviously this will not work as an inverter. Yeah, but suppose if we want some buffer, okay, suppose if you want to make some buffer, then can we use this? This is buffer, right? Basically, you are giving logic 1, output also logic 1. So it is buffer. Suppose then see, eventually two inverter, if you connect back to back, that forms one buffer, right? Yeah. So let's say we want to make a buffer. So can we use this?
we don't know the voltage as the at the S terminal. So we can't say that the transistor is in cutoff or is it is
Which age? Which age, Vayan?
S of I mean
Yes, yeah, yes. Right, your thinking is right. Yeah. See here, what Shubhayan is trying to say is this one. As this transistor is on, so the capacitor, the voltage across the capacitor will start building. So it will start building from 0. 1 volt, 2 volt, 3 volt, 4 volt. Fine, right? But think about it. Say this NMOS threshold voltage is equal to plus 0.5 volt. Okay, so it has reached up to 4 volt, fine. Now it has reached up to 4.5 volt, that is also fine. Now the question is, can this potential go beyond 4.5 volt? Can anyone answer? Can this potential go beyond 4.5 volt? Of course, no. Because see, to make this transistor on, you have to have at least VTH in here drop, right? Who has not understood this point? Okay, so let me uh, put one inverter before my question. Who have understood this point?
Yes, sir.
Okay,
Yes, sir.
so yes. Then Alisha, have you understood?
Yes, sir.
Okay, so could you please explain?
Uh, so if my voltage of the source goes above 4.5, so it goes to 4.6 volts, then
Right.
automatically the top transistor goes into cutoff. So
Cut off, right? So it cannot rise the potential anymore, right? So the maximum voltage that you can go here is up to 4.5 volt, right? Or in general way, the maximum potential across CL would be VDD minus VTHN, right? So obviously, again here, the output voltage will be less than one threshold voltage, will be one threshold voltage below that of the supply voltage, right? Okay. So this clearly explains why NMOS is not a good choice to be used, to be used for, to be used, to be used as an pull-off network, right? Okay. So let me write that as well. This explains why NMOS is not a good choice to be used as pull-up network. Okay. Now, similarly, can you explain why PMOS is not a good choice to be used as a pull-down network? Yeah. So for that, let us say we are using something as a pull-up network and we are using a PMOS as pull-down network, right? It is V in, it is V out, and here is this load capacitor CL. It is VDD. So again, when this V input is equal to 0, right, means 0 volt or logic 0, right, then obviously this transistor would be in on or off. My God. Yeah, tell me, this transistor would be in on or off?
So on.
Why?
So there should be some initial charge on V like CL.
Mhm,
Yes, sir.
mhm.
So VGS
Right,
would be then negative.
right, right. So this is basically this, right, right, VGS, right? This is gate, this is source, this is drain, isn't it?
Yes.
Yes.
Right. So here, as you can see, this is 0. So this transistor is on. So there is no issue. It can discharge, right? And the voltage can fall from VDD towards 0. But the minimum voltage here cannot go beyond
VTHP.
VTHP, right? Because once it reaches to VTHP, this transistor become switch off, right? So this is the minimum potential across CL. This is the minimum potential across CL. Okay.
Sir, Sir, shouldn't it be minus VTHP?
Please tell me why it should be minus VTHP.
Because VTHP is negative.
VTHP is negative. So here, say this is VTA. Okay. Say that it has it is changing from 5 volt, and say the threshold voltage VTHP is equal to minus 0.5 volt. Okay. Okay. And I think I understood. You are saying that this should be minus of VTHP, right?
Yes, sir.
Uh, yeah, because VTH value is negative, right? Yeah, VTHP value is negative. Yeah, that way you are right. Because say it is minus VTHP equal to minus 0.5, so that way minus of minus 0.5 would be plus 0.5, right? So V output minimum would be plus 0.5 volt only, right, across CL. Beyond which PMOS will be off, right? So these again explain why. So this is why PMOS is not a good choice for as a pull down network, right? So other two one I am not explaining, means why PMOS is a good choice for pull up network, because that we have already seen, because there is no issue. So if there is no issue, then PMOS is good as a pull up network. Similarly, NMOS is good as a pull down network, because we have not seen any issue here. But this explains why pull up and pull down network we cannot interchange, right? Any doubt so far? Okay, very good then. So again, this is a CMOS inverter. This is the transistor representation, NMOS, PMOS, not representation actually. This is the cross section of this transistor. I have again drawn because this will be helpful. Okay, while we are trying to make the voltage transfer characteristics out of it. Okay. So again, the body terminal we are not considering for the time being. We are only focusing on these top three terminals, not on the back terminal. Okay. So here, this is the NMOS characteristics, and here it is the PMOS characteristics. So let us see for NMOS characteristics. Let us say that the VDD is equal to 2.5 volt. VDD can be, VDD keep on changing depending on the technology node. For some technology node, VDD is 5 volts. For some technology node, VDD is 2.5 volt. For some technology node, VDD can be even as low as 1 volt, right? Because when we are shrinking these devices, shrinking means you are changing this gate length, right? At the same time, you have to also scale down the supply voltages, right? Because each material has a particular breakdown voltage, right? So when you are reducing this, you have to also reduce the supply voltage. Okay, so what is the relation from one technology to node to another technology node? We will discuss these things later on. But as of now, it is please just keep this thing in your mind. As the technology node is shrinking, means we are going for lower and lower channel length. At the same time, we have to also reduce the VDD. So if in some place, if you see VDD equal to even 0.9 volt, so don't get surprised. If you see 1.25 volt, don't get surprised, because you have to also consider that probably we were referring some different technology node. Okay, so say VDD equal to 2.5 volt, so it is NMOS, and say the threshold voltage VTHN equal to plus 0.3 volt, and for PMOS VTHN equal to minus 3.5 volt. Okay. Okay, so for NMOS, we have started rising our VGS, right? So that way up to 0.3 volt, up to 0.3 volt, there will be no current. So once you increase it a little bit more, current will increase. Let's say for 0.5 volt, the current is like this. Up at 1 volt, this 1.5 volt, 2 volt, 2.5 volt, and VDD is 2.5 volt, so we cannot go beyond this, right? Okay, fine. Now see this. This is gate voltage. This is gate voltage. This is source voltage, right? This is VGS, and VGS is nothing but V in. Am I right? Okay. So that way V in equal to VGS equal to 2.5. So that means whatever voltage we are writing here, that is basically V in, right? Okay. Now let us shift our focus from NMOS, that is this one, to this PMOS. Okay. So what is happening in PMOS? Something is interesting that is happening in PMOS. So for PMOS, threshold voltage is minus 0.3. So we have to reduce the gate potential from 0, then till minus 0.3, no current. Minus 0.5, yes, VGS minus 0.5, some current. VGS minus 1 volt, current increases. Minus 1.5 increases. Minus 2 volt increases. Minus 2.5 increases further. We cannot obviously go beyond 2.5 because the maximum supply voltage is 2.5. Now you might be thinking, then why we are getting minus 2.5? Because we are considering 0 to 2 point, because we have a supply voltage which is one is the ground rail, there is 0. Other one is another VDD power rail which is of plus 2.5. That is because, see, once you have given V in equal to 0, right, then what is happening? This is gate, this is source. So this is VGS. So it is VGS is becoming 0 minus 2.5 volt. So that's become minus 2.5 volt. So that's how we are getting minus 2.5 because it is VGS. I remember that S is already connected with VDD, which is equal to 2.5. Right? So gate becomes 0, so that becomes VGS becomes minus 2.5, right? Okay. Now here is the interesting. How can we relate this VGS for this PMOS with this VIN? Let's see, who can tell me? How can we relate this VGS for PMOS with this VIN? It's very easy, but still I am asking.
VDD minus V.
So this is basically what we have to do. We can write here, it is V in. Yeah, what you have to do, please tell me once again.
So VGS is equal to VDD minus V.
Okay, so can I write
Sorry, the
this?
V minus VDD, not VGS. Yes.
Yeah.
Yes.
So can I write this?
Yes.
Yeah. So V in equal to VGS plus VDD, right? So that way, for this one, what would be the V in for this line? Hey, please tell me. Otherwise, it looks like I am only. Huh? It would be 0, right? For this, hey, you should tell me. Otherwise, it's it's like only I am talking.
0.5.
Yeah, it should be interactive, right? So at 0.5, this one is 1 volt, this one is 1.5 volt, this is how much? 2 volt, right?
Yes.
Have I missed something? Should I have one more? Here, how many lines? Here, 3, 4, 5. 5 lines, but here we are getting up to 0.5. Then here, is it correct? Yeah, it is
Yes.
correct, na? It is
Yes.
correct only, right? Huh? Right. Yeah. So when so I think for your understanding, I will draw one more line. So what will happen when this VGS is equal to when this V in is equal to 2.5 for PMOS?
It will be in cutoff.
All right. So you will get like this, na?
Yes.
Right. So let us write that as well, huh? So this is for V in equal to this. This is for V in equal to 2.5, right? So similarly, this plot is for VGS equal to 0. No, this is for VGS equal to 0, right? Okay. Yes. So now, again, our goal is to get the VTC from this, graphically first. Then you know what is the technique. This NMOS technique we have to keep as it is, and we have to keep take these characteristics and superimpose these characteristics on top of this. So please suggest how am I going to do this? Please suggest quickly. Tarun?
So like the previous cases, we can flip the second graph.
Right.
We can superimpose with the first graph
Superimpose with the first graph.
and
Exactly.
the intersection.
Yeah, exactly. Exactly. We can do that. So how then the curve would look like? Yeah, it is bit type of not so easy to draw it and properly get the VTC, right? So let us do it step by step. Otherwise, we will miss couple of points. Okay. So let us first take this VGS of 0.5, right? So VGS is equal to V in. So basically, V in equal to 0.5, right? So V in is equal to 0.5. So here V in is 0.5, this one, right? So this is V in 0.5, or should I do it like this, or should I come from? No, I think I should do it like this only. Yeah, I think I should do it like this only. Yeah. So let us first focus only this. Okay. VGS equal to 0.5 and means V in equal to 0.5. So for V in equal to 0.5, the characteristics for this NMOS is like this, but for PMOS it is like this. So it should be near to the this fourth line, right? So I have to be careful while doing so.
Sir, you can draw each V in with a different color.
Each V in with a different color. Okay. So, okay, let me choose a red for this. Okay, I will use some different color for different. Okay, that is a good idea. Okay, so as you have suggested, so this is V in equal to how much 0.5 volt, right? Okay, say okay. Then we have increased it to 1 volt. So for okay, before I go to that, so here it is this for V in equal to 0.5 PMOS, and for NMOS, this is the characteristics, right? This is the characteristics for or when this V in is equal to 0.5. So what is the intersection? Then you have to take the intersection of this for the same V in only, na? So the intersection of this line and the intersection of this line. So this is this line, this point, right? Of so this is this point, right? Okay. So if I draw so many things, it would be like hodgepodge later on. Okay. So let me just keep it like this. Okay. Neil, choose one more color. Next color maybe green. Okay. Now let us say now we have shifted to 1 volt. So we have shifted to 1 volt, right? So for NMOS, okay, maybe this would be better if I do it like this. So for NMOS, it is like this. And to make it similar to the this one, let me make this one as. Are you getting what I am doing? This is for PMOS. I am doing the same color on top of it so that you can understand it. Okay. So this is for V in equal to 0.5. Right now we have moved to V in equal to 1. So V in equal to 1 for this is this, and V in equal to 1 is for this, right, which is below to this. So what I have to do, I have a characteristics probably something like this. right? Something like not very good characteristic. This one probably I can do something better. Yeah, this one, right? So here again you have to take the intersection between this green one and this green one. So this comes out to be, the intersection is this, right? So this is for V in equal to 1 volt, right? And let us again take some other color. So let us then shift to V in equal to 1, V in equal to 1.5. So for V in equal to 1.5 is, for here it is this one, this blue one for NMOS, right? And for PMOS it is this one which is below this, right? Right. So you have to take the intersection between this blue and blue. So this blue and blue intersection you can see, oh, it is here, right? Ah, so it is here, right? So it is here. So this blue one we have writing here V in equal to 1.5 volt, right? Okay, let us choose one more color, maybe the pink one, and go for the other one, that is VGS equal to 2 volt. So VGS equal to 2 volt means this one, right? So let us draw this pink color here, and VGS equal to 2 volt is this one, that means the second line, not second line, is the first line, right? Is the first line, so it should be somewhere here, right? So it is here. So here you can see the intersection is now changed to this. Okay. Now two extreme points. So first of all, let us move to V in equal to 2.5. So V in equal to 2.5. Let me take the orange color. So V in equal to 2.5 is this one. So this is V in equal to what? 2.5 volt, right? I think the pink color I have not mentioned. So pink color, let me use this. For pink color, it is V in equal to 2 volt. And here this V in equal to 2.5 volt. But for PMOS, 2.5 volt stands for this only, right? This only. So for PMOS, it is this line, right? Okay. So what is the intersection? Intersection is here, right? So intersection is here. Okay, I think we have missed one point, which is for VGS equal to 0 or V in equal to 0. So for V in equal to 0, for NMOS, the characteristics is like this, right? But for PMOS, for V in equal to 0, the characteristics is this one. So that way we have the characteristics like this, right? And basically it will intersect here, right? So as you can see from here, as we are changing, so this is for V in equal to 0 volt. So see this, when you are changing from V in equal to 0, the output is, what is the output? So here this VDS is nothing but this V output. So the output is 0. Please take a note of this. Sorry, not 0. This is equal to VD, right? So when this V in equal to 0, where is the intersection? The PMOS is this one, NMOS is this line, right? And they intersect here. So the output is equal to VDD, right? Now you change to from V in 0 to zero point 0.5. So V into 0.5, PMOS characteristics is this one, and here NMOS characteristics is this one. Intersection is here. So it is slightly below this VDD, small little bit below VDD, right? Okay, now you go for 1 volt. So when you get V in equal to 1 volt, PMOS characteristics is this one and NMOS characteristics is this one. Intersection is here. Again, slight reduction in the output voltage. Then go to the next one. Okay, increase it by again by 0.5 volt. So go to 0.5, so it is 1.5 volt. 1.5 volt PMOS characteristics is like this. 1.5 volt V in NMOS characteristics is this one. So where is the intersection? Intersection is here. Now see here the beauty. The beauty is all of a sudden the intersection has changed from this side towards this side, right? Earlier it was very close to VDD, but now it has immediately shifted from VDD towards near to the very zero, right? Okay. So at 1.5 it has become quite close to zero, not equal to zero, but quite close to zero. Now let us move it further. V in equal to 2 volt. So V in equal to 2 volt, PMOS characteristics is this one, but NMOS characteristics with V in equal to 2 volt is this pink one, right? So that gives out this intersection, right? Where is the intersection? This intersection. So it has eventually now closer to, much more closer to zero, right? Now finally, when this V in equal to 2.5, you have a NMOS characteristics like this, but PMOS characteristics is, PMOS is off, so PMOS characteristics like this, which gives you the intersection exactly as the origin intersection. So that means when V in equal to 2.5 volt, you will get 0 volt at the output. Similarly, when this V in equal to 2.5 volt, V in equal to V in equal to 2.5 volt, like for this case, right, you can see for NMOS at that time NMOS is off, so the intersection is here. So output is 0. Output is VDD, right? So you can clearly see from here the VOL dash, that is equal to 0 volt, and VOH dash, that is equal to VDD. So that is again one of the our requirement, right? That we should get the full swing, right? And that is actually we are getting the full swing, right? So that requirement is fulfilled. What about the static power consumption? Static power consumption, we have seen it's not there, because once the PMOS is off, only the NMOS is on. Once the NMOS is on, PMOS is off. So both in steady state, both the transistors are not on at the same time. So there is no direct path in steady state from VDD to 0, right? So no steady, no, sorry, not again, not steady state. This is a static power dissipation. So no static power dissipation, right? So I am saying steady state means basically you are not changing the input. Okay, input is either fixed to 0 or 1. It is not switching, right? So that criteria is also been fulfilled. No static power dissipation. So V out minimum voltage is 0, V output maximum voltage is equal to VDD. So that is also been satisfied, right? What are the other drawbacks that we have seen in earlier case, right? So the area requirement, again, that is not an thing, because we are using only the transistors only, right? So there is no resistance part. So the area requirement is also that way, criteria is fulfilled. So as you can see, then why this CMOS is so popular for making digital ICs? Because of this reason, right? By using this type of circuit, we can achieve so many, means we can actually overcome so many difficulties that we have seen in earlier cases, right? So let me also write quickly here some of the things. Advantages. Number one, no static power dissipation. I am putting one star here. Why? Because if I say no static power dissipation, technically that is not correct, because these transistors, we say this transistor leakage current is 0, ideal transistors. So, but that is not actually the case. All transistors are like ideal, not the ideal transistor, practical transistor. They do have leakage current. So considering that, when if you keep it at 1 or 0, there will be very small amount of power dissipation even in the when you are not switching. Okay, so that gives rise to some static power dissipation, but it is not due to the direct path between VDD and ground. Okay, so no static power dissipation, number one. Then V out is equal to V output swing is from rail to rail. Rail to rail, you understand, right? That means 0 to VDD, right? The complete swing you are getting at this output, and this is steady state power point. So these are the two most important, advantage. We will also see some of the other advantage as we go along in our discussions, right? So from here, I think now it's the time to draw the voltage transfer characteristics based on this diagram, right? So what will be the voltage transfer characteristics for the CMOS? V output, V in. Yeah, and let us also indicate the number here. So this is region 1, this is region 2. No, this is not the correct way to do it. This is region 3, region 4, region 5. Okay. Yeah. So I'm requesting you to please tell me what would be the region of operation in this region for this BTC. So I hope that you will agree that it should be like this only, and that is also clear from this, right? So please tell me in region 1, what would be the region of operation for both NMOS and PMOS?
Cutoff and trial.
First one is cutoff. NMOS is cutoff.
Yes, cutoff and trial.
Yes, NMOS is cut off.
Right. Try it. Then region 2,
Saturation and trial.
saturation, triode. Then
Saturation.
sat. Yeah, please tell me quickly.
Then linear and set.
Triode and set.
Okay, linear or triode, sat. Here,
Linear and cutoff.
sorry.
Linear and cutoff.
Linear or triode and cutoff. Right. Again, these regions, you should know in which region the transistors are operating, because that would help you to analyze them analytically, right? If you have to find some of the equations, and from those equations you have to find the values, right? So for numerical problems, this is very important, right? So you should know that for up to this region, that is for this region, right? Here this NMOS is off, right? So only the PMOS is in triode region. That also you can see here. NMOS is off, PMOS in the triode region. So you can find what should be the relation here. Similarly, if you consider for region 2, here it is NMOS in the saturation, that you can see NMOS are in saturation in this region, but PMOS are in triode region, saturation and triode. So that way you should be also able to find the output versus input characteristics here, right? The third one, that is for this case. So that is in this region. So in this region is basically this region where there is a huge swing with a small huge swing in the output voltage with a small swing in the input voltage. So that is primarily, this region, right? So this region is very sharp and very, steep fall will be there, right? So this region, both the transistor would be operating in saturation. So you can equate these two regions which are in saturation, and you can find the relation between here. So suppose if I have to find what is the threshold, my switching threshold for this transistor, how will find it? If I have to find the switching threshold for this, do you recall what is switching threshold? Switching threshold
Yes,
is you
we
have to
draw a
take,
line Vout equal
right,
to V.
right. You have to take an curve of V in equal to V. Yeah, please.
Then the cut point will be the switching threshold.
Sorry, could you please explain it again? I think I
The
missed it.
point the point where the two graphs meet will be the switching threshold VT.
But how do you find it analytically?
I have the equation of both. I mean both the transistors in saturation. So
Right.
Kn of Kn into VGS minus VTH square equal to Kp into VDD minus Vin minus mod of VTH square. So
Mhm.
from there
Yeah,
I will Vin equal
right.
to V and
Right. From there, you have to put V in equal to V out. Then that way you have only one, yeah, only one equation and only one variable, right? And you solve for either V in or V out, and that will give you the switching threshold.
yes sir.
Yeah, Shubhan, isn't it?
Yes sir.
Ah, right. So switching threshold. Right. So I request you to please try to find out the switching threshold in terms of this Kn and Kp. Okay. So in terms of Kn and Kp, please try to find the switching threshold for this CMOS inverter, because it is quite simple, right? And in region 4, that is in region 4, okay, if you see from here, region 4, that is this region. Now here, this transistor is in linear and saturation. Again, you know the equations, so that you can find what should be the slope, curve, and all these things, right? And region 5, this PMOS is off, only the NMOS is in operational. So NMOS is in triode and PMOS is in actually in cutoff, right? So that way you can also find like what should be the, means no need to find, because here you can easily see this is zero output voltage. But if eventually in some case if you need it, so you can always, you should know that which regions the transistors are operating in. Okay, here and here and all this. Okay, so here I think last one more minute I will take. Just tell me if I have to find what is VIL. Okay, so how can I find it? VIL. Anyone? Rahul, Aniket, Jangam, Abhishek.
Sir, we have to find the point where this enter the region 3. Just enter the region 3. That we
Right?
will.
How you will find that? You remember slope you have to make -1.
Yeah, yes.
Okay, so but what will be the region of operation in that
Uh,
particular case?
3.
The
Are you
region
sure?
2.
Are you sure it will be 3?
It's at the edge of region 3.
See, yeah, but at in 3, when both the transistors are in actually saturation, the sharp, this fall will be very high. So that means the slope is much higher than, the mode of slope will be much higher than 1, right? So it should not be in region 3, it should be in region 2.
Okay, sir.
Okay, similarly for VIH, it would be in region, again in region 4. Right. So, okay, I request all of you to please try to find the switching threshold for this. Okay, and we'll start from our discussion from here only. So we have started the main discussion of our digital IC design. So from here onwards, like things will move on, or we have to build up. Okay, based on whatever we have discussed. Okay, all those things are also not type of like time pass that we have done. They are also very, very important in terms of our basic understanding. On top of that, we will build our knowledge on this digital IC design. Okay, then. Thank you very much. So it's almost 12. So you have definitely have some class after that. So we'll meet in the next class and I will see you in the next time. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.